This is Fundamental Problem 15-16. In Fundamental Problem 15-16, the ball strikes the smooth wall with a velocity of 20 meters per second. If the coefficient of restitution between the ball and the wall is 0.75, determine the velocity of the ball just after the impact. They give us the coefficient of restitution, so we would like to use equation 1511, but this is oblique impact and not central impact, so there's something important we need to know about equation 1511. If you turn to page 269 in your textbook, they tell us that the coefficient of restitution relates the relative velocity components of the particles along the line of impact. So if the line of impact is along the x direction, then these are the x components of the velocities. So on your equation sheet, you should make a note that these are the components along the line of impact, and that is important when you have a problem with oblique impact. So keeping that in mind, we can use equation 1511, and I have the ball colliding with the wall. The wall is not going anywhere, so let's call the wall object A. Its velocity after the collision is 0. Its velocity before the collision is also 0. Then I have the ball. I know the initial velocity, but in my equation for the coefficient of restitution, it is the x component of the velocity. So here's the line of impact like this, which is perpendicular to the plane of contact, which is here. So the initial velocity of the ball is 20 meters per second. The x component of that is 20 times cosine of 30 degrees. The final velocity of the wall is VB2, that's what I'm looking for, and the x component would be VB2 times cosine theta. But if I do this, they show me that the velocity is this way. This is in the negative direction, so I should stick a negative sign in there. Okay, so I know the coefficient of restitution is equal to 0.75, so now I can say minus VB2 times cosine theta is equal to 0.75 times negative 20 times cosine of 30 degrees. Let's make both sides positive. And 20 times cosine of 30 degrees times 0.75 is 12.99. So the x component of the ball, ball's velocity after the collision is 12.99. Now we can also use conservation of momentum. Conservation of momentum is a vector equation. We can use it in the x direction. We can also use it in the y direction. Let's look in the y direction since we already have the x component of the ball's velocity. So here we have the collision. During the collision, the ball exerts a force on the wall and the wall exerts a force on the ball. Those forces are in the x direction. So in the y direction, we have no forces. So we can say the mass of the ball times the velocity of the ball before the collision in the y direction, so that would be times sine of 30 degrees, so that's this component of the velocity. The wall's not going anywhere, so its momentum is equal to 0. The impulse is equal to 0. Now, I didn't do anything with gravity in this problem, but I also don't know from the picture whether I'm looking straight down at the ball or if this is the side of the wall and down is pointing this way. So we're going to ignore gravity. And even if I don't ignore gravity, the impulse that I would have for the force of gravity during the time of the collision would be very small. And then I have the mass of the ball after the collision times the velocity of the ball after the collision, and this would be the sine of theta. That component's pointing upwards, so that would be positive also. Well, the mass of the ball cancels out, so it doesn't matter whether or not I know what it is. The initial velocity of the ball was 20, so this is 20 times sine of 30 degrees is equal to VB2 times sine theta. 20 times sine of 30 degrees is 10. So the y component of the velocity is 10. I was asked to find the velocity of the ball just after the impact, so I need the magnitude and the direction. VB2, since I have the x component and the y component, I can find the magnitude by doing 12.99 squared plus 10 squared and taking the square root, and that gives me 16.39, and the units for that are meters per second. And for the angle, this is the cosine component, this is the sine component. Or I can say if I want the angle, I take the inverse tangent of the y component, which is 10, over the x component, which is 12.99, and that gives me 37.6 degrees. So I have the magnitude and the direction for the velocity of the ball after the collision, and that concludes fundamental problem 16.